Hello, and welcome back to my YouTube channel. My name is Professor Govalla, and today I'm going to be talking to you about capacitors. Specifically, we're going to dive into this capacitor equation here and this capacitor image, and we're going to talk about what a capacitor is used for, and we're going to do an example towards the end. So what is a capacitor? A capacitor is a passive element or device designed to store energy in its electric field, and it's constructed by any two conducting bodies, regardless of their shape and size, separated by an insulating dielectric or medium. And I'm going to go ahead and post a video that I did in the past of me making a capacitor, but essentially the conducting bodies, like for example here and here, could be in practice or normally could be aluminum foils. And this dielectric located here, it's getting a little messy, could be anything from air to paper to a component called mica. All right. And essentially, if you fold this up, so if you have one plate being aluminum foil, this is mica or air, and then this is another aluminum foil, and you put a wire here and you read the capacitor reading, you're going to get a capacitance between these two plates. So let's dive into the integral equations of a capacitor. So essentially, when you attach a voltage source to a capacitor, there's source deposits a positive charge at one of the end of the plates and a negative charge at the other end of the plate. And this is set to store charge. So charge being Q is equals to C times the voltage, where this C here is what we refer to as the capacitance, and it's measured in farads, which is in honor of microfarad. And essentially, we want to dive into what capacitance is. So if I'm going to go ahead and zoom out here, and I'm going to write here, capacitance is equals to what's called ER, A over D, where A, capital A, is the surface area of the plates. And as you can see, this means that the larger A is, the larger my capacitance. Okay, so for A goes up, C goes up. Okay, and the next term that it depends on is this D term, which is the distance or the spacing between the plates. And essentially, as we can see here, when D goes down, or let's say when D goes up, C goes down. So D goes up, C goes down. It's the inverse. And we have this epsilon, so epsilon R, which is called the relative permittivity. Of a material. And essentially, this is a very important concept, but here we have that if epsilon R, or I'm going to call this ER, goes up, the capacitance goes up as well. So if a material permits an electric field to pass through it easily, then the capacitance becomes higher. Okay, so let's dive into this relative permittivity because it's a very important concept. And I'm going to say that ER is equals to epsilon over epsilon naught, and where epsilon is the electric permittivity of the material, the electric permittivity of a material. Again, remember, this is electric permittivity versus the relative permittivity. Okay, so then this here becomes the permittivity of a vacuum, or of, let me just call this a free space. A free space, sometimes called a vacuum. Again, the key word here is permit, right? In a vacuum or in free space, charge is attracted to one another very, very easily. So that's our reference point. And then any material in terms of air or in terms of water has its own electric permittivity. And you can look this up on a table. So we want to divide that over to get the relative permittivity of a material. And that is what we put into our capacitor equation. So an example of this is air. Again, just to make this clear, if I have air and I have a plus and a negative charge, these are attracted to each other a lot easier than, let's say, if I had water and there's a positive charge and a negative charge, right, being attracted to them. So water has a higher permittivity, or relative permittivity, compared to air. The next general equation for capacitance, which we're going to study, is, or we're going to mention, is that C is equals to the charge over the voltage, right? And that's coming from this equation here, right? Which we said that essentially that the charge stored on the capacitor is the capacitor times the voltage. So as a result, we can write the capacitance as the charge divided by the voltage. And this states that the ratio of charge on one plate of a capacitor to the voltage difference between the two plates. So essentially, if you have a capacitance, which is equals to 1 farad, right, we can say that this is 1 coulomb per 1 volt, right? And again, this is a change in voltage, right? All right, so what I want to do now is I want to do a little bit of a quiz, and this is essentially just diving into some review of the coulomb. So if we say that, so this, let me say this is a quiz, all right? And essentially, how many electrons make 1 coulomb, right, of charge? So if you can answer that question in the comment section below, that'll be good. So again, the question is, how many electrons make up 1 coulomb of charge? So what we can say is that, so you can pause the video and answer it, but I'll answer it now. I can say that a charge, or a single electron, a charge or a single electron, let me call this QE, is equals to 1.60 times 10, 02 times 10 to the negative 19 coulombs per electron. Okay. And this coulomb is named after a French physicist, Charles Augustin de Coulomb. So just that's honoring him there. So this means that 1 electron carries this many coulombs of charge, right? That's a very, very small amount. And then to find 1 coulomb, we need to find out how many of those tiny charges do we need to make 1 coulomb? So essentially, if you did some chemistry or prerequisites chemistry, you would say 1 coulomb over 1.602 times 10 to the negative 19 coulombs over electrons. And essentially, this cancels out with this. So then this becomes 6.242 times 10 to the 18 electrons. So essentially, what is this saying? This is saying that, therefore, you need about 6.242 quadrillion or quintillion electrons to make 1 coulomb of charge. So essentially, this is how many electrons are passing through, right? Per change of 1 volt to get 1 farad in our capacitance. All right. So I'm hoping to kind of amaze you by this number, right? It's a lot of electrons passing through to make 1 coulomb of charge. So the next thing I want to talk about is how we can describe capacitance in terms of current and voltages. So what do we know from our previous lectures and our previous videos? We can say that the current is basically the change in charge, so change in Q over a change in time. So if you have a resistance and you have, again, the 6.24 quintillion electrons passing through, so that change in charge over a change in a given time, let's say 3 seconds, gives you a current, right? So that is the definition of a current, right? And we know that charge is dependent on the capacitance times the voltage through the capacitance. So what we can do is we can go ahead and replace Q over here. And we could say then that current is the change in C in capacitance times the voltage over dt. And the capacitance is just a value, right? It could be 1 farad or 3 farads, or it's normally like microfarads actually. So we can go ahead and pull that out. So C times the change in our voltage over the change in time gives us our current through a capacitor. Again, it could be depicted like this, right? So this change in voltage, this is our capacitance, and this is our current, I. So what is this telling us, right? We want to basically grasp what this equation here means, right? And essentially what it's saying is that voltage across a capacitor cannot change instantaneously, right? But the current can, right? So what does that mean, right? For something to change instantaneously. So we'll go ahead and talk about the current changing instantaneously first. So for example, let's say that my change in time, dt, which is equals to change in time, is equated to 0. Then dv over dt is equals to dv over 0, which is basically goes to infinity. All right. So this is talking about a situation where time is extremely close to 0, right? Instantaneous. Again, in applications, time can't really be 0 because, right, time is always moving. But in this situation, imagine time is extremely close to 0, so it's instantaneous. So this means that, so current, I, is equals to C over dV over dt, which is C times infinity, which is equals to infinity. So if my change in time is instantaneous, very, very close to 0, my current shoots up, right? Shoots up straight to infinity. Okay, it's But again, this is limited, right? This is limited because we cannot actually have a time equals to 0. But the idea is that we're showing that our current can shoot up instantaneously to infinity as time equals to 0. So the next example, the next limit we're going to take is consider my dV, my change in voltage, to be 0. So again, this is no change in voltage. So I hope we all know what this means. If we have no change in voltage, this is a DC voltage. Then we can say then I is equals to C dV over dt. So then this is C times 0 over dt, which is equals to 0. So therefore, a capacitor, in this case, if current is 0, right, what does this mean? This means that the capacitor acts as what? The capacitor acts like an open circuit in DC, right? So essentially no current. So imagine if I have a battery connected to a capacitor, basically current can't flow through this, right? There's going to be buildup of charge here, but then other than that, it's just going to build up the charge and nothing's going to happen. Okay, it's going to be an open circuit. The next thing we want to consider is we want to represent voltage. So we want to go ahead and represent V of t in terms of I of t. So represent Vc of t, or the voltage across the capacitor, in terms of I of t. So what does that look like? So we know that I is equals to C dV over dt. What I can say here then is that dV over dt is equated to I divided by C. And then we can go ahead and take the integral on both sides and do dt here, right? Obviously, this dt cancels out with this dt. So we have dv is equals to the integral of I over C dt. And we can go ahead and I made a mistake here. This does not work like this. So essentially what we have here is we take the integral on both sides, and we go ahead and multiply both sides by dt. That's what we do. So dt and dt. This cancels out with this. This cancels out with this. And this remains. So then we have v is equals to the integral of I over C dt. We can go ahead and put some limits on here and take out the c because it's just a constant. So v is equals to 1 over c integral from 0 to t 0. Or let's go ahead and say that v is equals to, or actually this integral is going to be from t0 to t, and then this would be from t0 to t. So as a result of that, we're going to get v of t is equals, or v of t minus v of t0 is equals to 1 over c integral t of 0 to t I dt. We can then go ahead and move the t to this guy to the right hand side. So then v of t is equals to v of t of 0 plus 1 over c t of 0 to t I dt. Consider that v of t0 is equals to v of 0 is equals to 0. So this means that t of 0 is equals to 0. So then we get that v of t is equals to 1 over c integral 0 to t I dt. And this is a situation where the capacitive voltage before, you know, time 0 is basically equals to 0. Okay. So capacitor, we call this capacitor, is uncharged. All right. And as you can see, since this is the voltage across the capacitor, it cannot change instantaneously. So depending on how my current flows, okay, depending on how my, let's say I have a an AC sine, this voltage here is also going to, it's not going to change instantaneously. It's also going to flow like a sine wave. Okay. And we'll do an example of that shortly. The last thing I want to talk about now is power. So power, instantaneous power through a capacitor, P of T, is equated to VI, which is C times, we know that I is V of T, D V of T over D of T. Again, consider that this is V of T times I of T. So essentially this right here is equated to this I, and this right here is equated to here. Okay. Go ahead and backspace that. So essentially when P of T is positive, where a positive power, this means that the capacitor is receiving power. The capacitor is receiving power or charging up. We call this charging up. And then the same thing. So where a negative P of T, the capacitor is this delivering power or discharging. So now consider this typical example you might have on a quiz or an exam. And it's saying that given this voltage through time, plot your current through a capacitor. And let's consider that my capacitor has a value of 0.5 farads. Go ahead and pause the video and see if you can solve it. But I'll go ahead and do it now. So essentially what I'm going to do is I'm going to write an equation or a function for V of T. And I'm going to say then that V of T, this is rise over run. So rise is 6 over run, which is 2t, from 0 t to 2. And from 2, let me not make this inclusive. So from 2 to 4, this is going to be 6. And actually 6 divided by 2 is just going to be 3. All right. The same thing happens here, but it's going to be in the negative direction. So negative 3t from 4 to 6, and then 0 otherwise. Okay, we can go ahead now, and I like to just write out my I of t. So I of t is equals to my capacitance times the derivative of my voltage in respect to time. So 3 times 0.5, right? So the derivative of 3t is 3. And you multiply by 0.5, this is going to give me 1.5. It's going to be from 0 to 2. The derivative of 6 is just 0 from 2 to 4. And the derivative of negative 3t times 0.5 is negative 1.5 from 4 to 6. And lastly, we have the derivative of 0, which is a 0 otherwise. So what does this plot look like? This plot looks like this. So I of t, obviously it says 0 otherwise, so I'm going to have 0 all the way to 0. Let me just go ahead and plot 2. This is 4, and this is 6. Okay, so then we can go ahead and say that at 0, again, this is where that instantaneous shift comes from. It shoots up, right? And it won't go to infinity because my time, again, is limited, right? But it will shoot up to this 1.5, and it will stay at 1.5. My current will stay at 1.5 until 2 seconds, where it stops changing because voltage was changing. So now it stops changing. So it's here from 2 to 4. So it's a DC voltage. So then I go down to 0 current. It shoots down instantaneously again to 0 current through. And then again, my voltage is changing again. So what's going to happen is I'm going to shoot down to the negative. Let me go ahead and do this. Call this negative 1.5. It's going to shoot down to negative 1.5 and just be at 1.5 because it's changing from 4 to 6. And then it stops changing, goes back to 0. So then my current shoots instantaneously back down to 0 and stays there. So this is the graph, or this is the answer. If you got the answer correctly, please let me know down in the comment section below. If you found this video helpful, please like the video, comment down, share the video, and subscribe to my YouTube channel. Thank you.